All right, so today we're talking about Chapter 3, Section 4, Optimization, Finding Absolute Maximum and Minimum Values. Now, obviously, we have done this before in the previous section, and there isn't really too much more to this particular section. Obviously, we're going to have one application problem. We're also going to figure out, kind of another way to figure out maximum and minimum. Um, well, we're not going to really figure out another way. We know that we're going to be using the methods that we should be familiar with. Again, going from college algebra or pre-calculus into this course, you should be pretty familiar with the concepts that we're about to go over. Now, of course, obviously, it's a nice refresher. Let's begin. All right, so let's talk about well, let's just go ahead and put this on the notes so I can put my laser beam everywhere. Alrighty, so looking at just some arbitrary graph here, excuse me, some arbitrary graph here. Um, this point down here, if we were doing derivatives from here, we would call that a relative minimum, right? It's a relative minimum, right? Never mind what's in the blue for right now. We'd call that a relative minimum, and then right here we'd call that a relative maximum, and then we'd have another relative minimum here, right? And again, the relative minimums and maximums, they occur whenever our derivatives are equal to 0, right? And then here at the endpoints, we have something different. Okay, so previously, whenever we would look at these graphs, we would look at graphs that did this, that shot off like this, right? And of course, that's why this would be the relative maximum, was because it is the maximum relative to your viewing window, as well as the whole point of it, the derivative at that point is equal to 0. Right, but we call them relative minimums and relative maximums because obviously this can go on up in here forever, this can go up here forever, and it's not really I mean it's now definitely you can tell it's a relative maximum, right? Because the maximum with these arrows, they shoot out to infinity. Well, if we close the interval, right, now we have just this little line here, and on this line, it should be abundantly obvious that now we're not going to no longer have relative minimums and maximums, but now we're going to start having absolute minimums and maximums. And absolute minimums and maximums are exactly what they sound like. We're no longer talking about relative, we're talking about this is the lowest point in the graph, this is the highest point in the graph. And we're going to be determining that for this particular section. And let's just put this on the first page as well. And again, this is not a definition that it should be new to us. So suppose that f is a function with domain I. Again, I just means interval. Then f of c is an absolute minimum for all x and I. Well, I'm sorry, it's an absolute minimum if the function at that value. Again, we're an arbitrary c in this particular case. If f of c is an absolute minimum, I'm sorry, f of c is an absolute minimum if the function at that c is less than or equal to all values of f of x for all x and I, which makes sense, right? It's the minimum if it's the smallest y value, right? F of c, you can kind of think of it as, a y value, right? Because a function at some number, right, some number x, it outputs a y. So that makes sense. If this y, if c1, right, the y value here at c1 is lower than every single y value on this graph, then it's the minimum. And then of course you can say the same thing with the maximum. Alrighty, next up we're going to have the extreme value theorem, and this isn't going to be the first time you see the extreme value theorem. It pops up quite often in calculus, and lucky for us, it is not that big of a brain teaser at all. Again, it's kind of one of those things that you can pretty much come up with on your own if you were prompted to, right? So looking at these two graphs here, okay. So the function f has an absolute extrema at c2, which is right here. Here's c2, and at b, which is down here, right? This looks like the absolute and relative maximum, and this looks like the absolute minimum. And the function g, so this is our function g, this line here. And again, we have these named. This is f, this is g. And the function g has the absolute extrema at c1 and c2. So looking at c1, it is an absolute and relative maximum. And at c2 is an absolute and a relative minimum. This leads us to the following theorem. So the extreme value theorem, a continuous function f, right? Again, that's just the name of the f. That, in this particular case, this is called f and this is called g. But again, like I've said before, f is just a default name for functions, like we use x as a default variable. So a continuous function f defined over a closed interval, some closed interval. Okay, so now we're talking about closed intervals that we've talked about. Well, say we talked about, but you should be familiar with them. We talk about domain. That's basically what that is. That's the domain. The domain from a to b, including a and including b. That's what a closed interval is. So let's start over. A continuous function f defined over a closed interval ab must have an absolute maximum value and an absolute minimum value over that interval ab. Which makes sense. If you close an interval somewhere, right, and it's continuous, obviously, it has to be continuous, then somewhere on that graph, you're going to have an absolute value, you're going to have an absolute maximum and an absolute minimum. Which makes, again, like I said, complete sense. If we took this particular graph here, and if we just snipped it from, let's actually get the marker out. If we just snipped it from there to there, right? That is the interval that we close it on. So we say, never mind all this and never mind all this. Then right here, this part of the graph right here, there's going to be an absolute minimum and an absolute maximum. Okay, so again, that makes sense. And like I said, the extreme value theorem, we're going to be using that quite often in I don't know about this calculus, but we use it quite often in all calculuses, honestly. But anyways, that makes sense. And then now we're going to have an algorithm, sort of, to figure out these maximums and minimums, right? Now notice it says maximum hyphen minimum principal 1. Well, obviously that means there's going to be at least more than one principal, and there's going to be two principles, but the second principle we are pretty familiar with already. Normally, I don't like to follow along with the book's algorithms and stuff. Going, this is step A, B, C, D. We're going to step them A, B, C, D as well, just to follow along, because I think this is pretty handy. But again, it's something that we are familiar with. But let's just start here. So if we're trying to find the absolute maximum and absolute minimum values over some interval AB of a function, we're going to first find the first derivative. That's pretty easy. Second, we're going to determine the critical values. Again, the way we determine the critical values is we take that first derivative, we equate it to 0, and then boom, we have our critical values. And then C, we're going to list our critical values as well as the endpoints. Okay, because again, this is a closed interval. So we're also going to list the endpoints. So, and then D, we're going to evaluate the function f of x, like the original function, for each of the values in step C. And then the largest of these is going to be the absolute maximum, and the smallest is going to be the absolute minimum. So I do like this particular algorithm, mainly because unlike previous algorithms, I don't know if it's this class or other classes, but normally I dismiss, step-by-step things, because like I said, it's kind of like a peanut butter and jelly sandwich. I mean, there are, you don't have to memorize, I gotta do this, I gotta do this, I gotta do this, and you can just, build one. So, but in this particular case, I think it is pretty handy. So let's begin. All right, so looking at this graph, or this function rather, what do we know about it really, honestly? I mean, it's a cubic function, so we actually know kind of about oh, maybe I should have snipped the interval there. I'm pretty sure there's an interval involved. Yeah. Okay, so again, we're just going to take a quick flashback to pre-calculus, and maybe this might help a little bit. But this is a cubic function. All right. Well, it's a third degree function. I know that it's going to have at most, like two maximums or minimums, because if you recall, and again, this is just something extra. This isn't anything involved in this particular case or in this particular course, but just something that we have learned about the behavior of functions. But anyways, it's a third degree polynomial, and we know that since it's third degree, we know that the end behavior of the graph is going to look something like this. Did I do that? I snipped the. I didn't snip the problem again. I don't know why I keep cutting that off. Over the interval. There. Anyways, I know the end behavior, is down up, something like this, because it's a third degree polynomial. I also know that it's going to have at most 2 turning points, because again, if you recall, the turning points are 1 less than the degree of the polynomial. Let's see, was there anything else I really know about this? Not really. At this point, we just have to build the function with zeros. Okay, so that was a fun little exercise that went nowhere. Anyways, let's proceed. So in this particular case, again, we're going to do step 1. Right, we're going to call that A. So let's go ahead and put that A here. A, we need to find the derivative. So in order to find the derivative, well, should be pretty easy, right? It looks like it's just going to be 3x squared minus 3. I love derivatives that I can just do in my head while I'm asleep. Okay, so that's my derivative. Step 2, of course, or step B, was to equate the derivative to 0, and then we will find our critical values. So let's equate this to 0. So we're going to have a 3x squared minus 3. We're going to equate it to 0, and let's actually do better notation here and actually denote this as the first derivative. Okay. And then we're going to equate the derivative to 0. It looks like what we add 3 to both sides, divide both sides by 3. We get x squared is equal to 1. Take the square root of 1, so we get x is equal to the positive and negative 1. Okay. Now step C was to list all the values, list the critical points as well as the endpoints. Okay. Well, let's do this numerically. So we're going to have a negative 2 because that is one of the endpoints. We'll also have a negative 1 because that is a critical point, a positive 1 because that is a critical point, and then 3 halves because that is the other endpoint. Okay. So again, all I did here was I listed my critical points as well as my endpoints. Because again, the endpoints very well could be a maximum or minimum as we saw on the previous page. And then D, we're going to evaluate the function. We're just going to evaluate the function at our critical points and to see, is it a big number or a small number? And then, of course, if it's the largest of the numbers, then it's going to be a maximum. So if it's the smallest, it's going to be a minimum. So what we're going to do is we're going to look for f of negative 2, f of, we'll just do 3 halves here. All right, there's really no rhyme or reason. I'm just putting my f of values here. F of negative 1, and then f of 1. Right. So I'm going to do some behind the scenes calculator work. All I'm doing here though is I'm just going to be plugging, and probably just in our head. Let's do this in our head. We can do this. No need for a calculator. All right, so we're going to plug this negative 2 in to this equation. Okay, well, negative 2 cubed, that's going to be negative 2 times negative 2 times negative 2, that's negative 8, minus 3 times a negative 2, so it's going to be minus a negative 3 times negative 2 is a positive 6, so it's going to be plus 6, and then plus 2, so we're going to end up with 0. All right, shoot. Let's not deal with 3 halves just yet, okay? F of negative 1, well, negative 1 cubed, that's negative 1. Minus 3 times a negative 1, which is going to be plus 3, so negative 1 plus 3. And then plus 2, so we're going to end up with a positive 4. F of 1 cubed is 1, minus 3 plus 2, that's 1 minus 3. Yeah, it's going to be 0. And then 3 halves, let me actually write this out so I don't lose track of my thoughts here. So we're just going to do 3 halves squared minus 3 times 3 halves plus 2. So we have 9 fourths minus 9 halves. So we end up with, we need to get a common denominator here. And then we add 2, 27. Oh, it's not 9. I'm sorry, it's not 9 fourths. I wrote that wrong. I was wondering why it got a little more complicated for the common denominators there. That should be it. Should be 27 over 8. And then now it's not minus 9 halves. We get a common denominator. And then plus 2. We should have 7 eighths. So 7 eighths. Alrighty. So that was step D. And then step C, well, wait, no, that is step D. Step D. We got the those critical points. We evaluated. Again, all we did was just simply evaluate these numbers from step C, and then looking at it. Okay, so now we're going to try to make some sense here. The largest number is going to be the maximum. So this is the maximum, right? Because 4 is the largest of all these. And then the smallest number is going to be, well, we have 0 twice. So this tells me that on this graph, we're going to have one maximum. The maximum is going to be located at the point -1 and +4. That's where the maximum is going to be located at. And let's put the laser, -1 and 4. And then the minimum, we're going to have two minimums. They're going to be located at -2, 0, and at 1, 0. Let's go ahead and snip the graph here. And there we have it. We see here at -1, +4, we do indeed have the maximum, which is what we saw here. And at 0, -2, we have a minimum. And at 0, and at 1, 0, we also have an absolute minimum. So our absolute maximums and absolute minimums. All right, so that was a pretty easy problem. And they don't get much harder than that. They really don't. It's just it's all things that we have been doing up to this point, and we're just putting it all together. Nothing new in this section. So this reads example 2. Find the absolute maximum. Did I misskip anything? Any words? No, not really. Other than, as we can see in example 1, an absolute maximum or minimum value can occur at more than one point. Alrighty, so find the absolute maximum and absolute minimum values of f of x equal to 2e raised to 3x over the interval, the closed interval of -2 to +1/2. All right, so let's begin. Okay, so the first thing we need to do is we need to find the derivative. Okay, so f prime of x is going to be well, 2e raised to 3x. We're really just focused in on the e to 3x, and the derivative of e to 3x is going to be 3e to the 3x, and then the 3 gets multiplied by the 2 to get to 6e to the 3x. I'm going to try and stay consistent. Let me put that in white. What I say, 6e to the 3x. Okay. All right, and b, all right, we're going to equate this to 0, and all right. So looking at this is why we look at the graphs of our exponential functions, and then learn about the exponential function. You know, we try to get really intimately involved with our graphs of our functions, because if you try to do this, right, what would you do? You would divide each side by 6 or something, and then you would take the natural log of both sides, and then you just be like, you know, you would eventually get to this thought process here. Well, the thought process is This is an exponential function. We know exponential functions go like this, right? We know that the range of this exponential function, right? If we did something like this, we know what the range of this exponential function is from 0 to infinity, not including 0. So this tells me that there is no solution to finding to setting this equal to 0, okay? Because it will never equal to 0. So we're going to put over here no solution. Right? There's no way that we'll ever have any sort of a 0 there. Right? So next up, we're going to do step C. Well, step C, if you recall, was to was it to I forget, was it listing it? Yeah, okay, good. What was to list my critical points and my endpoints. Okay. Well, I had no critical points from step B, so all I have to do is list my endpoints, and my endpoints are going to just be, looking at the um, interval here, it's just going to be a -2 and a 1/2. Those are my only points I need to list. And then step D, and we are going to do some calculator work here. Can't do this one in our heads. Step D, we're going to have to find f of -2 as well as f of 1/2. Okay, so let me put this into the handy dandy calculator. All right, so 2e to the 3 times a -2. So we're going to get about, let's change these to abouts, little squiggly equal signs. All right, to about 0.00, and we'll round that up to a 5. I'm pretty sure that's what the book's wanting us to do. And then we're going to say 3 times a 1/2, and we've got 8.963. So 8.963. Okay, so let's see. Let's go back here and let's actually write maximum and then minimum. And then we'll do that for this as well. All right, so looking at this, we obviously, 8.963 is larger than 0.005. So this is going to be a maximum. And 0.005 is going to be a minimum. And then, of course, let's go ahead and look at the it's right there. Look at the graph. Okay, looking at the graph here, we have. Right, and again, notice how we indeed do have our exponential function, right? We know that it behaves like this. We know that we're not going to have any sort of a turning point here. And we see that, on the interval from -2 to 1/2, we're down here at -2, up here at 1/2, we do indeed see that we have the absolute minimum here at -2, which is going to be 0.005, which I guess is 2e to the -6. And over here at positive 1/2, we have the maximum of 8.963, which can be expressed as 2e to the 1/2. Okay. All right, so I will put this on the notes, but again, it's exactly what we have done before, looking at the second derivative. All right, so just to refresh your memory, suppose that f is a function such that the derivative of f of x exists for every x in an interval I, and there's exactly one critical value c and I for which the derivative is equal to 0. Then, if I take f of that critical point, I'm sorry, f of that critical point is going to be the absolute maximum value over our interval I if the second derivative of that value, of that critical point, is less than 0. Okay, so again, remember, if the second derivative is less than 0, we have a maximum. If the second derivative is greater than 0, we have a minimum. All right, now looking at this, and I think this might be where some confusion in this particular lecture can come from. Um, but I'll try my hardest to really explain this through. But it reads that theorem 9 holds no matter what the interval is, whether it's open, closed, infinite in length. So if the second derivative of if the second derivative of our function is equal to 0, then we must be at a maximum or minimum. Okay. So notice how earlier I said there are two principles. We did principle 1, and this is principle 2. Now, I know that as a college student, you kind of want tasks, right? You want tasks. You need to do A, and then you need to do B, and then you need to do C. Well, sometimes in mathematics, especially the higher up you go in mathematics, things aren't laid out as simple. Instead, you have to figure out the best way to solve a problem. All right. So for right now, let's purge this from our thoughts, and let's go straight to example 3. And then maybe I can really show you what I mean by, um, you know, which principle do we use. So we'll put, we'll do A first. And so in this particular case, let's go ahead and, this is kind of awkward. So we're going to list, we're going to we're doing problem A right now. Okay. But we're also going to be listing them in A, B, C, D like we have been doing. Okay. So we're going to put that in yellow, A. So the first thing we need to do is we need to get the derivative. Well, the derivative looks pretty easy. It's going to be 4 minus 2x. 4 minus 2x. And then b, we're going to, oh shoot, let's be more precise with our notation. I don't know why I do that a lot. I want to say 4 minus 2x. And let me make sure that I did that. Okay, good. All right, so 4 minus 2x. All right. Next up, let's equate this equal to 0. So we're going to have, oh, man. I know it probably doesn't necessarily matter to you what color I put in what, but I like to be a little bit consistent. So then we're going to set this equal to 0. All right, so this means we're going to subtract both sides by 4, divide by 2, so this is going to just be x equal to 2. Okay, negative divided by negative. And then step C. Okay, so this is where, well, that doesn't really matter here. All right, so step C, again, we're going to be listing the endpoints and the critical points. All right, well, for this particular interval, notice our interval is from negative infinity to positive infinity. We can't list those as an endpoint. Okay, so the only thing we can do is just say 2, right? Because that's it. Now here's where you kind of have to know which principle to use, principle 1 or principle 2. All right, but the thing is, it's kind of clear because, and let's go back. Let's just look at the first two examples, in fact, okay? So the first two examples, the first example had 4 numbers, 1, 2, 3, 4, I had 4 numbers. I evaluated all 4 of those. And of those 4, all right, one of them had to be the highest, and at least one of them had to be the lowest. And so we had a maximum minimum value, so we evaluated all 4. Okay. Now let's look at example 2. Example 2, we had 2 numbers. Okay. Well, evaluating those 2 numbers, of those 2 numbers, one of them had to be the highest, and one of them had to be the lowest. It has to be, right? You can't have the exact same for a maximum and minimum value over some interval. Some, I guess, I guess it wouldn't really be over an interval if it's just one number, huh? So yeah, you have to have a maximum and minimum value over some interval. That you just have to, right? And so we evaluate those 2. Well, now look at example 3. We only have one number. Well, I mean, depending on what I get, I don't know if it's going to be the highest or the lowest number, right? And that's why we have to use the principle 2 in some cases, because we have no other choice, right? If we evaluated, and let's just go ahead and evaluate, just to do it. Let's go ahead and evaluate. So let's now evaluate at f of 2. Okay. Well, f of 2 is 4 times 2 is 8 minus 4, which is 4. Okay. Well, I don't know if the point 24 is a maximum or minimum value because I have nothing to compare it against. Right? I don't know if it's the highest number or the lowest number. I have nothing to compare it against. And so that's why principle 1 kind of breaks down sometimes. And so we're going to have to move to principle 2, which was take the second derivative of that critical point. Okay? So we're going to take the second derivative, and we're gonna actually not call this d because I don't want to get confused with our principle 1. What should we call this? I don't know. Maybe d point. D point. No, we just won't call it anything. I mean, if you're watching the lecture, obviously you can follow along. So we're going to take the second derivative. Okay, f double prime of x is going to be equal to, well, it looks like it's going to be, I mean, I'm taking the derivative of this. That's pretty easy. It's just going to be negative 2, right? Okay, it's just a constant negative 2. Well, this is kind of cool. So um, if I take the second derivative and it's, well, the second derivative is going to be negative 2. Doesn't matter what I put into it. It tells me that it's going to be a relative maximum. Okay. Now again, of course, you can do this. Let's go ahead and, just for notation's sake, let's go ahead and put a 2 in here. It's still going to be negative 2, right? Because there's no x value for me to plug in. So this tells me where we're going to have a relative maximum. Actually, looks like it's going to be an absolute maximum, huh? It looks like we're going to have an absolute maximum. And then that maximum occurs at, we said 4, right? So the maximum occurs at 2, 4 when we evaluated earlier. So let's go ahead and break out the graph. And of course, there we have it. Okay. So that's kind of where, the different types of methods, I wouldn't say break down, but there you have two choices, and honestly, at the end of the day, you're gonna know which one to use. It's not gonna be hard. Okay, so let's do this again, and let's instead. Actually, I don't know if I can just. Let's just not clip it. Let's just do this. All right. So now we're going to work on b. All right, and then the first step, what we did again was we got the derivative. So f prime of x was equal to 4 minus 2x. And then b, we did, we equated it to equal to 0. Oh no, man, I hate this. I don't know why I keep forgetting. And then step C, this particular case, all right, now since we have endpoints, now we can actually, we can list our critical points and endpoints. Not too bad this particular case. So we have a 1, again, I'm just listing these in order. And then we have the critical point, which is 2, and then the other side of the interval, which is 4. And again, these numbers, 1 and 4, are just these endpoints. And then what we're going to do is we're going to take the function and evaluate it at those values, right? So step D, we're going to do f of 1, f of 2, they're all positive? Yeah, I guess so. And f of 4. Okay, let's do this in our head. F of 1, and again, what I'm doing, I'm just plugging these values into my original equation, right? Notice how it said f of x. Sorry, this is f of x. I'm saying f of this. We're not doing the first derivative or the second derivative. We're just evaluating the function at those points. Okay. Well, we already know f of 2 is equal to 4 because we did that in the first example, right? And then f of 1, 4 times 1 minus, that's equal to 3. F of 4, 16 minus 16, which is 0. Okay, so looking at this, it looks like this 4 is going to be my maximum. And right here, what do we do? Blue? We did blue. We have the minimum. So at the point 2, 4, we have a maximum, and at the point 4, 0, we have a minimum. And of course, we'll see that right here. Okay. Again, it's the same thing. It's the same graph of 4x minus x squared, except we snipped it and the domain to only be between 1 and 4. All right, I think 2 more problems here. All right, so find the absolute maximum and absolute minimum values of our function. So first thing we're going to do, we're going to get the derivative. Well, the derivative here is just going to be 3. So f prime of x is just going to be 3 and then x minus 2 squared. And of course, and then we take the derivative of the inside of x minus 2, which is just going to be 1. So we're just stuck with this. Now we're going to determine critical values. No, yeah, we're going to determine the critical values, which is going to be, we're going to set this equal to 0. All right, so we divide both sides by 3. This is pretty darn easy. We divide both sides by 3, that goes away. We take square root of both sides, that goes away. So we're just going to end up with x equal to 2. All right, step C. All right, step C, we're going to list our critical points. Well, our critical point here is only 2. Okay, and same as problem A on the previous example, we have one critical point. We don't know if it's a maximum or minimum because we have nothing to compare it to. So let's go ahead and take the second derivative here. And the second derivative of our function is going to be f double prime of x is just 6 x minus 2. Okay, so now let's take the, do that. Yeah, okay, good. All right, so now what we're going to do is we're going to take the critical point and plug it into our equation, f of positive 2. And if I plug it into our equation, I end up with, well, looking here, if I put a 2 right here, I should get 2 minus 2, which is 0, and then 6 times 0 is 0. So f del prime of 2 is 0. Okay, so we have a little bit of an issue. This is something we haven't run into before, but let's just go back and look at some definitions here. So looking at this one, all right, what we did was we plugged in our critical point into our second derivative. All right, so notice how the first part of the theorem is that we have an absolute maximum if the second derivative at my critical point is less than 0. We have an absolute minimum if the second derivative is greater than 0. We have no rules for what happens when the second derivative is equal to 0. And that's what we got here. The second derivative at our critical point is equal to 0. So this tells us that, well, tells us what you think it does, that there is no maximum or minimum to this particular function. And I think that's pretty cool. And of course, we can see that over here. We do indeed not have a maximum or minimum. Right? We just kind of we change from an inflection point down to an inflection point up, or I'm sorry, concavity down to concavity up at our inflection point there. And that's it. There's no maximum, no minimums. All right, so next up, and I'm pretty sure lastly, we're going to be talking about a business model. And this is pretty interesting, I think. It's also, it's also pretty easy, right? And again, like I said, when I was a student, I see word problems, I just think, man, I hope there's not a lot of these on the test, and then I'd be on my merry way. But I was a very lazy student at first, and so let's do this the easy way, right? Instead of the hard way of not doing it and then failing the test. So this reads the cost of materials, C, so C is the cost of materials in dollars, to produce X dozen birthday cakes at Yum's Bakery is given by our function, which is C of X is equal to 0.5x squared plus 40x plus 200. So A wants us to find the average cost, which is C bar, the bar over the C. C bar of X is equal to our function over X. Well, that couldn't be any easier than I have no analogy, sorry. All right, this is pretty easy. So all we have to do is take our C of X, which is this. This is our C of X, and we just have to put it over X. That's it. So my function is going to be C bar of X. I'm just dividing X by every one of these terms, right? So it's just going to be 0.5X plus 40 plus 200 over X. That's it. Like it literally just told us what we had to do there. Just divide it by X. B gets a little more complicated, but not abundantly so, because obviously it's going to be stuff that we have done in this section so far. So we want to find the minimum average cost and interpret the results. Okay, so in order to find the minimum average cost, all right, that's going to be a critical point, right? Because we're talking about maximums and minimums, so we're going to have to find a critical point. So let's go ahead and start this process. A, we're going to take the derivative. So the derivative of C of X, or of this, so C bar of X is going to be equal to, well, this is going to be 0.5 plus, and the 40, the derivative of 40, well, that's just 0. And then 20 over X, if you've forgotten, let's go ahead and do this real quick. We know we can rewrite this as 200x to the minus 1. Okay, and then if you recall, what we do is we put the negative 1 out front, and then we go down 1. Okay, so it's a negative 1 times 200, so this turns into a negative 200 times x to the negative 2, which we know can now turn into a negative negative 200 over x squared. Okay, so if you forgot how to do it, that's how we do that. And we're going to be doing it again, but we're going to do it in our head next time when we get to second derivative. Okay, so it's not going to be 0.5 plus, it's going to be minus because, again, like I said, we had to get that derivative right. So minus 200 over x squared. Okay, so again, that was step A. Step B in our little algorithm we had is we have to figure out what the critical points are. So we're going to have to set this equal to 0. So 0.5 minus 200 over x squared is equal to 0. All right, so all right, let's take this slowly. So 0.5 is equal to a positive 200 over x squared. All right, let's multiply both sides by x squared. So we're going to have 0.5x squared is equal to 200. Divide both sides by 0.5, so we have x squared is equal to 400. Right, and then we're going to take the square root of both sides, so we're going to have x is equal to plus or minus 20. Okay, so we have plus or minus 20. Let's see. Yeah, okay, good. Alrighty, so we have plus or minus 20, and well, we can't use both. We can't use plus 20 or minus 20. So let's go back and just use some common sense here. All right, we have x is equal to plus or minus 20. Well, what was x? What was x in our equation? Well, x was dozen birthday cakes. Okay, well, don't know about you guys, but I've never seen a negative dozen birthday cakes, right? Now, of course, jokes can be made, whatever, but we don't technically ever see a negative birthday cake. So we're not going to be taking the negative 20, we're going to be taking the positive 20. So let's put a, no, that's not right now. Okay. Anyway, so we go to C. Now let's do it. Let's just mark it off right here. That way, to avoid any confusion. All right, so now what we're going to do is we're going to list any endpoints or critical points, right? Well, we don't really have endpoints because we're not told we're not really told what we let's just go ahead and put it down to actually follow along, I guess. All right. So again, we have the same problem that we've had before, where we don't really have anything to compare it to. So if that's the case, now we're going to have to take the second derivative. And the second derivative isn't too hard because obviously 0.5 just kind of disappears, and then we end up with a well, let's just go ahead and let's continue this on the next page. Okay, so let's see. So let me write the first derivative down real fast. Okay, good. Okay, so that means the second derivative is going to be, let's see, prime. Second derivative is going to be, again, the 0.5 goes away. This turns into a 3, so it's going to turn into a negative. No, it's going to turn to a positive, sorry, positive. And it's going to be 400 over x cubed. Okay, so we have 400 over x cubed. Now let's take the second derivative, and we're going to input our critical point from the example, which is 20, positive 20. So it's 400 over 20 cubed. Oh gosh, 20 cubed. There we go, 20 cubed. And 20 cubed, I mean, it's a big number, but it's not really what I'm worried about right now. The big number, obviously, it's going to be greater than 0. Okay, so since it's greater than 0, I know that that is the absolute minimum, which is what I'm looking for here. Okay, so now what I'm going to do is I'm going to plug in, so C bar of 20 will get me, again, C bar, that's the original function we had, which is up here, and let's just put this into the calculator. It's 60. So C bar of 20 is equal to 60. All right. So what does this tell me? All right. So because again the problem says find a minimum average cost and interpret the results. All right. So the minimum average cost is going to be $60 per dozen. Right. X was a dozen, so $60 per dozen is the minimum cost for this particular business model. And what does this mean? Well, it means that is the minimum amount of materials, right? The baking materials, 20 dozen, that I should make to maximize my profit. And let's go ahead and snip the graph. Like so. And of course we do indeed see this is our function, and at the point 2060, we do indeed see that that is a critical point. Okay. And let's let the book say it a little bit more succinctly than I could. And then the summary. And that concludes today's lecture.